Okay, physical science time. Today we are talking about really what is the crux, the central point, the central element of chemistry, which is chemical bonding. Aiden, can you tell from the monitor there if this color is showing up on the whiteboard at all? Yeah. Okay. Good. The objective, which I would like you to write down with me as I write it down. You should write it down too. I hope your notebook is out so that you can note take in your book of notes. Don't forget that your review work, and especially this worksheet. Today we're going to talk about the stuff that will help you with that worksheet. I would really appreciate if you did that. I hope that you have waited to do it until now, because it would be so easy to just get them all from online, but you wouldn't learn anything. Anyway, the objective is diagram the patterns of change in chemical bonding. Diagram, so we're going to be doing drawings with labels. The patterns, repeating cycles, of change, you know what change is, I think, in chemical bonding. And that brings us back to our title. Ideally, the outline of what I would like to talk about today is why bond, and then the various types of bonds, which are ionic, covalent, I'm going to put metallic, even though we've already kind of talked about that one, and then we're going to talk about naming. This will be where we spend most of our time, and formulas. Well, I'm going to spell it formaluse because that's how it came out. Formaluse. Okay, again, Aiden, will you tell me, is that picture in picture? Like there's a big one of the whole board. Okay, good. I had this idea of writing down the outline. I'm drawing all over myself. I'm writing down the outline because I thought it might help you. But now I realize that I might have also shot myself in the foot by kind of showing my hand. And if I don't get to any of these, one, it'll help me remember them, but two, if I don't get to any of them, then it's going to make me look like a fool. But guess what? That's what I'm here for. That's the main reason I'm here. I actually can't stand to be made look a fool. So let's start out and we'll see what happens. So why bond? Why would things, and we're going to define what things do this in a second, but why would things bond? Let's think about it in the broader sense. Can you think of an analogy maybe in your little human life that might be analogous to bonding? What's something that would be like bonding in your life?
Bonding?
Yeah, bonding, okay. But could you be more specific?
With friends.
Yeah, with your friends. That's what I was thinking. I was thinking of marriage because I only have one friend and it's my wife. Well, I have two friends, but one of them is Jesus, and he's not like, I can't give him a high five. So my wife and I are bonded. You and your... Don't feel like I should say that on public YouTube. And also that implies a plural that I don't think even you wish you would have said. But could we say brethren? That guy. You guys are bonded in a sense. What is the question of what bonds you is also the question of what holds you together. So in this class, what holds you three together? And when your whole group isn't suspended, what holds you guys together?
You.
Thank you. Yeah, but what holds you together? This is actually, I'm going to clap back at you, literally clap back. Even when it's forced, because that is something that does happen, even when it's forced, what is holding you together? The kind of idea of lab partnership is what I'm getting at. Like you and your lab partners are held together because you're in the same group. Like you kind of sink or swim together. Like either all of you have a good lab, even though some of your write-ups are terrible, or all of you have a bad lab because you're together in it. Same over here, and especially true over here because there is some weight pulling over here and some people who don't pull their weight. But that's something that bonds you together, something that holds you together. So a bond is something that holds together. My wife and I are held together by, not physically by our rings, although there's a lot of times there is a physical symbolism of bonding, but we are held together by the idea that we are going to choose to be, married to only each other and exclusively each other. That's part of the aspect of marriage, that we are going to choose only the other person for our lives. When you get married, if that ever happens to you, that's how it'll be. If you are, what's another way that we use bond? Not necessarily in relationships. When else might you use the word bond? Exactly. Yep. If we were to, for instance, bond two 2x4s together with glue, they're held together by that glue. Okay. So then there's a bonding agent. I'm kind of, this is not like a science term or a term, even a general term, but some agent, a thing that does. That's what an agent is. Bonding agent, a thing that holds together. So in the case of the wood being glued together, the glue is the bonding agent. In the case of these chemical bonds, we'll see that electrons are the bonding agent. You could say symbolically that in my bond with my wife, our rings hold us together, are the bonding agent. In y'all's lab, the concept of your lab bonds you together. Your friendship with each other bonds you together. That's such a beautiful thought. You're held together throughout space and time by the power of friendship. And gravity, technically. So why would things bond? And here's the last part of this little topic. Why would, especially when we're talking about things, but we're going to now shift it to what our primary focus, which is the periodic table of the elements, which is the atoms. Why would atoms bond with each other? It kind of relates to the other ideas, the kind of philosophical ideas we're talking about. But atoms bond to what? Why?
Get more electrons.
Not necessarily more, but
Get electrons.
not necessarily get. To stabilize, not always gain, but to bond, to achieve, let's put it that way. That's something that many of you don't know anything about. Oh, God bless you. I shouldn't have said that. That wasn't very nice. Achieve stability. That's the goal. That, we might say, is the chief end of the atom. The reason it's raison d'etre, the reason that it exists is to achieve stability. So the example, and we'll move right into ionic bonding now. The example, this color show up okay, Streety? No. Okay, let's pick a different. Let's pick brown. This is orange. Let's pick orange. Okay. Well, this is orange, which is, it kind of looks brown because it's green and orange now mixed together. But so to achieve stability, so let's think about some atoms that might ionically bond. Remember from last time, I don't know that we talked about this in the video, but we definitely talked about it during the chapter review and even during the test, that an ionic bond is made, or is made between a metal, you know where to find metals, I hope, and a non-metal, or one or more metals and one or more non-metals. So let's check out, let's put down a metal. Can you give me an example of a metal? Ideally from one of these first two groups. Ideally, instead of that, from one of these, we could do a tin, but let's do one of these first two, it'll be easier. Strontium, okay. So we've got strontium here. I'm going to draw the electron dot diagram for strontium, which you should know how to do. It's strontium, its symbol with how many valence electrons it has around it. It has 2, it's in group 2, and so we draw it with 2 valence electrons. Now, what is the number of stability on the periodic table?
8.
Yep. On the periodic table, you can just write this underneath what you were already writing. 8 valence electrons is stable. For all of them? For all of them?
Yes.
No. There are 2 exceptions. Hydrogen and helium. For them, 2 valence electrons is stable. We don't really consider those exceptions to the octet rule. Remember, this is called the octet rule. We talked about that last time. The octet rule. We don't consider them exceptions to the octet rule because in its fullness of expression, we would say that the octet rule is the atoms are more stable with 8 valence electrons, except hydrogen and helium, which are stable with 2. We just consider that to be part of the octet rule. So they're not really exceptions, they're just specific circumstances. So strontium would be more stable if it had 8 valence electrons. How many does it have? 2. So how many electrons total does it have, though? Does it have only 2 electrons? No, and that's one misconception, because people think that since we draw them like this with the electron dot diagrams, that if it lost these two, it would have none. But that's not true at all. If it lost these two, it would now have 36, which is the same number as krypton, which is a noble gas, which means it has 8 valence electrons. Another way to think about it is that if strontium lost 2, right, if it loses 1, it'll have as many as rubidium, of 1 valence electron. If it loses 2, it'll have as many as krypton, which is 8. So an easy, maybe not necessarily easy, but an achievable way for strontium to become more stable is to lose these 2 valence electrons. Remember, that's one of the ways we defined metals, is that they lose electrons to achieve stability. Why? It can just do that, right? Nope, that's another misconception. It can't just. The analogy I always use, you can watch my videos from the past, I've probably said this 5 times on YouTube. The analogy I always use is just like your parents wish you would leave their house, but they can't just get rid of you. They just can't just put you on the street. They can't just be like, see ya, Mason and Haley and Peyton, bye. They have to make sure you have somewhere relatively safe to go. So college, a new house, a marriage, a job, whatever. They have to make sure you have somewhere to go first. Same with strontium. It can't just say, see ya, electrons, have fun in outer space. That has to have somewhere to go. So these can't just leave. They can only go to a place. Does that kind of make sense? I know like there's a difference there. So what would take these 2 electrons from strontium? Something else. What do you think wants them? That's the wants, right? We say things like achieve stability. Okay, what gas? And we don't say gases. We say, you're thinking of non-metals. Oxygen, great suggestion. Because how many does oxygen have? Let's do this in a pink, whatever, sure. How many does oxygen have? You said 6. How many does oxygen want? In parentheses or in quotes. We don't, yeah, oxygen doesn't want anything. Consciousness has not been proven to exist on that level of physics, but there is discussion. But we say things like want as like a shorthand for is more stable with. So oxygen is more stable with 8. It has 6, so it could gain 2. And this is easier to see. Just like in a similar way to strontium can't just say see ya 2 valence electrons, oxygen can't just manifest 2 valence electrons out of outer space. It can't just create 2 valence electrons. So it can only take them from somewhere. And in this case, I put those arrows, but now I'm going to erase them and put the orange electrons that were around strontium now around oxygen. So now, how many does oxygen have? And how many does strontium have? Don't say 0. How many? It has 8. Right, what were its valence electrons are gone, and so now it has 8 valence electrons because its next layer down has 8. So what was its lower level electrons are now its valence electrons, and it has 8 also. So both of these are more stable because they've satisfied the octet rule. Both more stable. That's why they bond, is to become more stable, as we talked about. And now this bond that has formed between them, between this metal and this non-metal, they're happy. They can just go on their separate ways, like a one-night stand, right? That's fine. See ya. Yes or no? No. No see ya. They are bonded because strontium has given oxygen those valence electrons. Now it has a what kind of charge? It used to have a neutral charge. All atoms, remember, are neutral. It had 38 protons. It has to. Yep. And it had 38 electrons to balance that out. And now it only has 36 valence electrons. So it now has what kind of charge? Specifically a 2 positive charge. It has lost 2 valence electrons, so it has a 2 plus charge. Oxygen, meanwhile, used to have 8 valence electrons, and now it has 10. Still has 8 protons, though, otherwise it wouldn't be oxygen. So it has a 2 minus charge. And what do we know about these charges? Positive and negative. Positive charges and negative charges, opposites attract. And so there's this force of electromagnetic attraction between them. They are both more stable and held together by the electromagnetic force. So they're both more stable and they're now one single thing, which we write as, I'm just going to put it in black, Now instead of being strontium and oxygen, it is now the substance, the chemical, well, I don't want to use substance, what do I want? Compound, strontium oxide. Kind of like in marriage, oxygen has changed the last part of his name, her name, I don't know. Now it's strontium oxide. And that gets us down, we've skipped a little bit down to 5. When we name or write formulas for these bonded substances, these compounds, we name them by their metal, for ionic, we name them by their metal, and then the non-metal changed to ide. So instead of strontium and oxygen, we now have strontium oxide. That's one way these can achieve stability. Another way, let's do this one in red. Another way, this is going to become messy. I don't know, I kind of like it. I think as long as you're watching it in order, the organization is implicit, I hope, because my guess is that when people come in and just look at it, they will think that a literal insane person did it. But I hope that as we're going through it, the organization is implicit. So covalent, like a co-worker, or when you cooperate, what does that prefix co mean? Together. So these are together. And what do you think valence is referring to? So it's covalent. We said co is together. What do you think valent refers to? Valence electrons. So from these two clues, just of what the word is made of, can you guess what's happening here? In this case, we had a give or remove and a take, right? Give and take, and they were held together by the electromagnetic force. What do you think is going to happen here? They're going to, what verb might we use? Combine, sure. There's another verb we often use for these. Yes, not false, but all of this is bonding. If you're going to have some valence electrons together with someone, if you're going to have a Subway sandwich together with someone, you are sharing. There we go. These are going to share electrons. These mostly happen between nonmetals. So where ionic bonds are between, I'm going to do this in the color I use for ionic bonding, metal and nonmetal, covalent bonds are usually between nonmetals. So if we have, let's just say two nitrogen atoms. How many valence electrons does nitrogen have? And how am I going to indicate that? Yeah, 5. And how am I going to indicate that in my diagram? Boop, 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 boop. Boop, 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 boop. Each one has 5 dots. And how many do they both want, by the way? I've asked you this so many times, I hope it rings true. They both want, in quotes, 8. Can you think of a way that we could reconfigure these dots so that they're sharing them so that they both have 8? I can, and that's because I've done it before. Can you think of a way to reconfigure these dots so that they're sharing them, so they're between them, that they both have 8? They can't, they will share some. How many are they going to share between them? Yep, each one's going to share 3. So this one's 3 are going to be there. This one's 3 are going to be there. And when I say there, this is not in physical space. They aren't necessarily, this is just the way that we indicate that. So now this nitrogen has how many? Well, let's count them. 1, 2, 3, 4, 5, 6, 7, 8. And how many does this nitrogen have? 8. And what's holding them together? Well, the electrons from both nitrogens are attracted to both nuclei, and so this proton, or the protons in this nucleus, are attracting all of the electrons, and all of these electrons are also attracting this protons. And so they kind of move together as a pile through space. How would we write the formula for this? This is another key part of our writing formulas. How would we write the formula for this? Well, it's in, of course, that's the symbol, but how many of them are there? You might have even seen this kind of, no, how many nitrogens are there, I mean? You might have seen this format before. How many nitrogens are there? in what we just drawn? 2. So we write N2. That's how we write the formula for this substance. For this, to call this a compound is probably not in the strictest sense true, but to write the formula for this, we would just write N2. The little baby 2 is called a subscript, and that we use that in formulas to indicate how many of something there are, and they go with the thing before it. So when you previously had written H2O, which we'll diagram that in a second, you know what H2O is. You've heard that water is called H2O before. That 2 goes with the H, meaning that there are 2 H's and 1 O. Let's draw a little diagram like that for this one. How many valence electrons did oxygen have to begin with? 6. Boop, 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 boop. You've seen I've drawn 6 dots. How many does each hydrogen have? 1. Boop, boop. Now, how many does oxygen have, or seem to have now that it's sharing? 8. And how many does each hydrogen have? 2. It has 2. So each hydrogen has 2. And how many is hydrogen according to the octet rule? And you see it's kind of like a Venn diagram. I don't know if this is showing up at all on the screen. It's pretty tiny, and maybe even in real life it's not really showing up. But you see it's kind of like a Venn diagram. These 2 electrons are shared between that oxygen and this hydrogen. These 2 electrons are shared between that oxygen and that hydrogen. And these 2 are unpaired electrons. So in covalent bonding, they share them, and the attraction between the electrons and the protons and the electrons of both or all atoms holds them together. That's a covalent bond. By the way, this kind of bond we say, yeah, just get out of here. This kind of bond we say is non-polar. It doesn't have poles. The electrons are shared equally. You should write this down. Equal sharing. In this one, the electrons are shared unequally. Why? Well, think about who is attracting more electrons, oxygen or hydrogen, and why? Oxygen. Why? Not that it needs more, but because it has more what? Well, yes, but that's not why it's attracting more electrons. That would be repelling. It has more what? Protons. So oxygen has more protons, and so it more strongly attracts the electrons, and so those electrons hang out more with the oxygen, giving it a partial negative charge on the oxygen and a partial positive. I'm going to write this a little bit bigger and not quite so squished up down there. This symbol I'm drawing is this Greek lowercase letter delta, which is partial charge. So partial positive on the hydrogen end and partial negative on the oxygen end. And this is called a polar, meaning it has bond. Polar bond, which is unequal sharing, which generates poles. Okay, and in metallic bonding, this will be, we kind of talked a little bit about naming and formulas, but we'll talk more about that when we do your worksheet. In metallic bonding, which I guess I'll do also in pink, it's just, guess what kind of things? Metals, yeah. In metallic bonding, it's very easy. If we have, for instance, any of the transition metals, let's say gold, I love gold, all it is that the nuclei of the gold are arranged in a more or less repeating pattern called a crystal lattice, and the electrons from all of them just kind of hang out around all of them, called the sea of electrons. And we talked about this in the last chapter. It was on the last test. But this sea of electrons is just that all the electrons are around all of the nuclei. And because there's a sea of electrons, there are several parts of its properties. It has usually very smooth surfaces, making it shiny. Electrons can flow easily, making it a good conductor. And if something moves, it just kind of stays where it moved to, making it malleable or ductile. And then finally, the last thing we're going to talk about is these naming and formulas. To write the name of something, as we said before, for ionic, we just call it first name and then last name changed to "-ide". And for covalent, we say how many there are. So if something is like SCl4, we call it sulfur. And then since there are 4 chlorines, we call it tetrachloride. And we'll talk more about those as we're going over your worksheets. There are rules for both, and we'll talk about them as we go over your worksheet. Do you have questions about, in general, chemical bonding? So usually when there's more time, I do go into detail about how we do this, but we'll do that at a different time since we've run out. But I think hopefully you have the conceptual framework of why and how bonding occurs in all these different types. And when I say hopefully, I think that that's true. I think you should after hearing me rattle on for 30 minutes. Bye. So that worksheet